All right, this is hour 2 for Physics 1C for November 5th, and we're going to be talking about displacement current. Oop, that was pretty... Okay, so we've used the name Maxwell in this class before, but this is the first time we're actually going to talk about something that Maxwell supposedly did, a calculation that he did. It's a really clever understanding of what's called Ampere's law. So we need to remember what Ampere's law is first. So Ampere's law stated that if I have, let's say for example, a wire that carries current in it. Okay, so I've got some wire, and let's say it has a current flowing this way. Ampere's law said that if I were to draw a path around my wire here, like this for example, that path, which encloses a surface, and let's use the simplest surface we can imagine here, that is to say just kind of a circle, a flat circle, okay? There's some surface that's produced here. Call it S1. So we're going to say that the path in this case is a circle, and we'll say it has a radius r, let's say. And the surface of the path, which I'm writing here to be S1, is, what would you call it? It's also really a circle. It's just a, well, let's say it's a disk. Is that the right thing to say? It's a disk? Compact disc or something like this, or a DVD. All right, so we've got our path, we've got our surface, and what Ampere's law tells us is that if we evaluate the integral of b dot dl around this path, that it is equal to the magnetic constant mu naught multiplied by the current that is enclosed. Enclosed is often the wrong way to say this, but I don't know how else to say it. It's equal to the current that flows through the path, basically. Okay, so if you have some current that flows through your path, then you get some quantity that we say is b dot dl, and we can use this to prove, for example, in this case, that there's a magnetic field that's produced where this path is here. There's a magnetic field, B, and it's circular in nature. At every point, it kind of points parallel to the path here. And this equation we can use to show that the value of that magnetic field is equal to mu naught multiplied by the current that's flowing in the wire divided by 2 pi r. That's just something that you probably used on a lot of homework problems. The magnetic field for a long current carrying wire, right? Okay, so what Maxwell said was that if you really think about what you're saying with this, it says that I need to perform a line integral around a path. That path, right, will always enclose a surface, right? Any path, as long as it's a closed path, has to have a surface associated with it, right? So what if you could manipulate what that path would be? Oh, sorry, what the surface would be. The path is fixed, but what the surface could be. And what I mean by that is, think about this. So imagine that I have a path, okay? And imagine that the path is like the edge of a trampoline or something like that, okay? So it's circular in nature. So I've got some path like this, right? I can imagine a surface for that path, just like we did in the previous part that's a disk, right? But if you put, for example, on top of a trampoline, like a bowling ball or something like that, right? If I put a big bowling ball on a trampoline, the bowling ball is going to cause the trampoline to kind of sag down, right? So I could have the exact same path in terms of its shape, right? But I can imagine a different surface. I can imagine a surface that's like lumpy in some way, like that. And now my surface is this kind of cone-looking thing, like looks like maybe like a black hole or something. I don't know. It's like but this would now be my surface. So you could have two different surfaces, one that we might call S1, and another one here that we might call S2. So it's the same path. The paths are identical. But the surface that we choose to use, okay, may look a little different. You forgot what this was called, but something similar was covered in Math 220. It probably had something to do with... I'm probably going to get this wrong. It's either Gauss's theorem or Stokes' theorem. In this case, I think it's Gauss's theorem. Does that sound familiar to you? When I say Stokes' theorem, you know what I'm talking about? That relates the... what is it? It relates... So Stokes' theorem is the one that relates a volume integral to a surface integral, right? Green's theorem. Yeah, one of the, I forget the names. This is something we will cover later in class. But I'm certain you learned something about this in 220 for sure. Yeah. What it would be, I don't immediately know, but you guys get the idea, right? You can imagine a surface that has a path like this, and then a surface that's completely different, but has the exact same path around its boundaries, right? Everyone understand that part? Anyone have any problems with visualizing that? So here's what Maxwell said then. Maxwell said, what if you apply this to a capacitor? What happens then? So let's take a circuit that we've looked at before. So we'll take a circuit that has just a battery, so some EMF for a battery right here, positive and negative side like that. And then we'll throw a switch into our problem, like there. And then, just for good measure, we'll throw a resistor in. And what else? Then what we're going to do is we'll put a capacitor plate here and a capacitor plate here. That should leave us enough room. Although, no, probably not. Let's scoot it over a little bit. So we're going to have the capacitor part of this is going to be overdrawn just because it's what we need to have in a certain way. So I've got a capacitor, and we'll say it has a capacitance C. I have a resistor over here, R, though it's not going to be important for our problem. And I've got an EMF for a battery here. Now, initially, this capacitor starts uncharged. Okay, so what we'll do then is we'll throw this switch right here at t equal to 0. So the switch is closed at t equal to 0. That's going to cause current to flow. Like this, right? And because this current is going to be changing in time, we'll call the current I like this, with the little I to represent that it's instantaneous current. And that current is going to flow in this direction, and it's going to cause charges to build up here, positive on this side, and negative charges will be built up on this side over here. And we'll say that at any point in time, the charge on our capacitor is little q. And this will, of course, occur, the flow of the current will happen up until the capacitor is fully charged, right? Okay, so here's what I hate that it does that. Shape, circle. So this is what Maxwell did. So let's draw a path like that. Do I have to use this? What I wanted to do is do this and then draw the black line going this way so that it's clear, maybe it's not so clear, that the path that we're choosing here goes around the wire, okay? So this is going to be our path, right? And in terms of the way that we would go around the path, we would go this way. Now, let's apply what we said about the two different surfaces to this system right here. All right. So, first of all, I could draw a surface that would be what we call maybe the easiest or the simplest surface to draw, which would be like a disk. And we'll call that surface S1. Okay? And we could go about using Ampere's law. And Ampere's law would tell us that there would be a magnetic field there because the current I passes through S1. And what I'm going to do is I'm going to call this current conduction current. Okay? So we're gonna put a little c down here to represent that our current in this case, I sub c, we're going to call that conduction current. Okay? So IC passes through S1, and as a result of that, we would say that the integral of b dot dl would be equal to mu naught multiplied by whatever that current is. Okay? And we have no problems. There would definitely be a magnetic field produced there. The magnetic field that's produced would point in the same direction as the path. No problem at all. That's what Ampere's law would say. But what if we choose this secondary surface here? So what if instead we take the same path, but we kind of make like a little hoop, and we go like this. And now we have a surface. Maybe we'll use a really fine line. Maybe that'll work for this. So now our surface is this thing. Like a net. Think of it as a net. Where this net, and we're going to call that surface S2. This net now, it goes inside of the capacitor and then back around right here, right? Okay. Now what we'd say is that the current that's flowing in the wire, I sub c, doesn't pass through S2. Which would mean that if I do integral of b dot dl, I would get, well, part of what Ampere's law says is that you need to take the current that goes through, oops, didn't need to do that. You need to take the current that actually goes through your surface. So the current here, what we called IC, our new surface basically is intentionally drawn in such a way that the current doesn't flow through it. So that means that if I do the exact same path, but I chose a different surface, I would get a different answer. In this case, I would get integral b dot dl is equal to 0 if I use S2. Does that make sense? And can you see that that's a problem? You're free. So if you go back to Ampere's law, if we went back, I wonder if I even wrote it down the right way. If we went all the way back here to when we first talked about Ampere's law, here's Ampere's law. This is what I said it was. It's the sum of all currents that pass through, this is the piece that's really important, any surface bounded by the path of integration. That any surface part is the thing that Maxwell took to heart. And Maxwell said, look, it doesn't work. This is an example that as soon as you use a really basic circuit element that we know a lot about, it doesn't work anymore because there's no current that flows in this regime right here. The current stops right here. But it turns out that you actually can get the same answer if you're really clever about how you do this. And that's what Maxwell did. He said, look, if you think about what happens in the space between these plates right here, right? If you think about what happens with the space between these plates right here, current can't actually flow from the positive to the negative side here unless the electric field just gets so big that there's a static discharge between the two of them. Unless you break the electric field strength of air. But what's happening in between the plates is that there's an increasing electric flux that's happening. And he thought you can think about that as being kind of similar to a current. I'm gonna pull this picture up here. Now I wanted to draw it myself, but just because I wanted to go through slowly what was going on, because I think the picture is like too much. But let's read what this says right here, and then we'll go through it showing how we can prove that we can fix this problem here. So here we have parallel plate capacitors, and it says it's being charged. The conduction current through the plane surface, so the plane surface is this one right here, is IC, but there is no conduction current through the surface that bulges to pass between the plates. So this bulging surface right here, there's no current that's actually going to flow through that. It's like a cup. The two surfaces have a common boundary, so this difference in ion clothes leads to an apparent contradiction in implying Ampere's law. Okay? Just kind of a nicer picture of the same concept, right? So this is what This is what Maxwell did to solve this problem. So Maxwell said, in between these plates, there is a changing flux. And it's not a magnetic flux, it's a changing electric flux. And we can even figure out exactly what it would be. Because, first of all, we know that if at any moment in time there's a charge Q on the plates, that the potential difference between the plates... Now, how do I do this? The charge Q on the plates... Let's just start with flux. That should be an easy enough way to get it, right? Let's see. So the electric flux is equal to electric field multiplied by area. The electric field between the plates, I believe, is equal to delta V between the plates divided by L. So I have to label some things now. L would be the length between the plates here. And delta V would also be the potential difference between the plates. The potential difference, delta V, we get from the equation that Q is equal to C times delta V. Right? So this would be equal to Q over C times L times A, where C is capacitance. But if it's a parallel plate capacitor, then C is equal to epsilon naught multiplied by epsilon naught A divided by the length between the plates. So this would end up being equal to Q over epsilon naught over L times A multiplied by A. Notice that, and there's another L right here too. So what did I do here? We started off by saying electric field between the plates is delta V over L. Delta V is Q over C. C is epsilon naught. It's this whole thing right here. The L's cancel, the A's cancel, and we end up just getting that the flux, this is kind of something that's familiar probably, ends up being equal to Q divided by epsilon naught. This actually is, it's like Gauss's law basically, right? It looks like Gauss's law at least. So then what we can do now is we're going to multiply this to the left-hand side and say if I just take epsilon naught and I multiply by the electric flux, that gives me the charge. Now, we know that the charge on the plate is increasing over time in this problem. So what we can do with this is we can say, if I take the derivative of both sides here, then the time derivative of the charge on the plates turns out to be equal to epsilon naught multiplied by the time derivative of the flux. And now this is really interesting, because for one thing, on the left-hand side of this equation, what we have is the time rate of change of charge, right? And this time rate of change of charge, what does that look like to you? What do you get when you take the rate at which charge is changing on a plate? In this, I mean, just in general, what is dq dt? What did we define that as? If we go back to a few chapters, it's coulombs per second, so it's amps exactly. This would be measured in amps, right? Which means the right-hand side also would be measured in amps. Yeah. So in some very strange way, this is kind of like a current, right? You know, I don't know what a good way to visualize this is. What we could do is just say this. I'll say what this is, and then I'm going to draw a picture to kind of back this up. So what Maxwell did was he said, let's define this to be displacement current. So this is ID. This is what we call displacement current. That's his definition. He says anytime you have a changing flux, it's kind of like a displacement current. So what he said was the conduction current stops at the surface of the capacitor, but the displacement current continues right on through. Oops. So in between the plates, there's something that he calls displacement current. It's not the same thing as conduction current. Conduction current only happens inside of a conducting wire. But a time-changing electric flux can be like a current in a way, and it can solve this problem. So even though there's no actual current that flows through here, he said maybe there's this type of displacement current, and this displacement current is something that's related to the time rate of change of flux. This is the way that I would think about it. You start off with these two plates, right? And at first, there's a little bit of charge on the plates, right? You've got some amount of charge. And that sets up an electric field. Let's say once you have those on there, we represent that electric field with one line, right? Then as the charges build up, you get more electric field lines. And then more time passes, you get more electric field lines, because that's how we represent electric fields, right? And as more time passes, you get more electric field lines. So that the fact that the electric field is changing with respect to time within this region right here means the electric flux is changing in time in that region, and as a result, there's this type of current. It's not really current though, right? It's current just given another name. It's not current at all, really. It's really a flux that's changing. And this is interesting to Maxwell because, well, just look at it. It's the time rate of change of flux. What does that make you think about? What does the derivative of flux make you think about? Where else have we seen something that has the derivative of flux in it? EMF, yeah. And Faraday's law, right? Faraday's law has time rate of change of flux, but it's just magnetic flux, right? So this is really interesting, and when we put everything together, it'll be really obvious where the symmetries exist, right? So this is what Maxwell said. You have to alter Ampere's law, and so this is now referred to as the Ampere-Maxwell law, because Maxwell made one change to it. The Ampere-Maxwell law says that if I do the integral of B dot dl, I'm free to choose any surface I want. Sorry, I always use ds. I'm just used to doing that. Your book loves dl though, so if we do the integral of B dot dl over a closed surface, it's going to be equal to mu naught multiplied by the... Now, we have to include conduction current, and we have to include displacement current. Okay? We have to include both of them. We can write this out completely then as integral of B dot dl is equal to... So what we'll do is we'll do mu naught times I, and that will just be our normal current, what we define by current up till now, plus mu naught, and now I need to multiply by displacement current, and this is displacement current right here, epsilon naught times d phi dt. So we do mu naught multiplied by epsilon naught, and then we put in here the time rate of change of the flux. And there is the full Ampere-Maxwell law, and the final of Maxwell's equations. It says when you do the integral of B dot dl, you get mu naught I plus, you have to include this term right here. You have to include this term. Because if you don't, then you run into these contradictions like we said. And that term is called displacement current. It's not really current. That's just the name that Maxwell gave to it, right? Electric current is a very specific thing. This just happens to have the same units of current. And it's related to the time rate of change of flux, which we know has the units of current. So it's like, why not call it displacement current? It has the same units after all, even if it's a completely different phenomenon. The effect of this is that in the region between the capacitor plates, there's actually a magnetic field that's produced. That's what this tells us. If you were to perform this operation of doing this path integral, but you made your path in between the plates, you would still get a magnetic field. And what that would look like is this right here. So here what we have is magnetic field lines and electric field lines, both of them between a capacitor plate. And, well, they talk about displacement current density. That's a completely different thing, but the idea is that the buildup of the electric field between the capacitor plates produces a magnetic field that's kind of circular in nature like this. This is some picture that we're going to come back to when we talk about what's called the Poynting vector. And we're going to try to figure out how is energy flowing in this system? Is it flowing into the system or out of the system? So there we go. It's the last of Maxwell's equations. So what we'd like to do now is we want to Trying to think if I want to say more about the Poynting vector. I'll wait till we get there. All right, so let's throw all of Maxwell's equations together then, and let's write down what they are. There are integral and derivative forms of Maxwell's equations. We're going to write down the integral form because that's what we've been using all semester. In a couple lectures, we'll actually derive the differential forms. Okay, so what are Maxwell's equations? They are Gauss's law. We'll call them Gauss's laws because there's two of them. There's Gauss's law for electricity, or electrostatics, which says that if I find the integral of E dot dA, that this quantity, and something I don't really do, but I probably should. This is really a double integral because it's a surface integral. This quantity is always equal to the charge that's enclosed within my surface divided by epsilon naught. And this is often referred to as electric flux. Gauss's law for magnetism says if I do the exact same operation, but instead I use a magnetic field, that this tells me that as long as I choose a closed surface for a surface integral here, that the integral of b dot dA is 0. This is often referred to as there are no such thing as magnetic monopoles. As long as I choose a closed surface, the number of magnetic field lines that come in will be equal to the number of magnetic field lines that go out. Okay. And then we get Faraday's law, which just today we learned the full version of this. Faraday's law tells us what happens when the flux changes, right? So Gauss's laws, if you'll notice what they do, they tell us just statically what flux is. Electric flux is related to charge. Magnetic flux is the same thing as b dot dA, but it's equal to 0 of a closed surface, right? So Faraday's law states that if I take the integral of E dot dl, that this is equal to the negative of the time rate of change of magnetic flux. We can even write this in a more complete way by actually writing the magnetic flux into this equation like this. Okay. And then finally we have the Ampere-Maxwell law that we just completely wrote out a second ago. Here, let's label these. This is 1, this is 2, this is 3. There's 4 equations. There's technically a 5th that's not usually included within them, but we'll write it down too. The last equation says, well, we just did the integral of E dot dl, so the last thing to do then is the integral of B dot dl. And what this one gives us is mu naught times the enclosed current plus mu naught multiplied by epsilon naught. And then in here we have the time derivative of the electric flux. But even this one can be written in a slightly different way. We can write it as mu naught times I enclosed plus mu naught epsilon naught. And then here we would write the electric flux. So it should be just... Oh, no, I messed up. Did it again, but this time I'm just going to shift it over. I need a derivative in here. So there we go. Those are the Maxwell equations, and we're going to kind of talk about them in general, and like the symmetries and stuff that exist between them. That's it. Those are Maxwell's equations, and we're going to talk about what they mean. So the top two describe electrostatics, and the bottom two describe what's called electromagnetism. And what you can kind of notice about these things is that they all talk about flux, right? They talk about electric flux and magnetic flux. The first two tell you what happens with electric and magnetic flux in static situations. The third and fourth one tell you what happens when those things change, right? When magnetic flux changes, you get an EMF or you get an electric field, right? And down here it tells us that when electric flux is changing, you produce a magnetic field. Now, one thing you can do is you can talk about what these equations look like in empty space. It's one of the things that we'll do in the last chapter. If you look at the way these equations look in empty space, where there are no charges and no currents, they basically look exactly symmetric with each other, right? So let's write down what those look like real quick. So in empty space, with no charges and no currents, right? This is what the equations look like. This makes them look, I think, very similar to each other. So if I do E dot dA, where there are no charges, I get 0. If I do B dot dA, where there are no charges, I also get 0. If I do the integral of E dot dL, I get negative ddt of B dot dA. And if I do the integral of B dot dL, again, if I'm going to say that charge is 0 and Q is 0, I get rid of this term right here. So then I just get, for this one, mu naught epsilon naught times the derivative of E dot dA. Now in that form, I think they look very, very nicely symmetric. Apart from some constants that show up, which those constants in different units you can make equal to 1 if you want to. You can see that these equations they're perfectly symmetric, right? They look exactly the same except for a minus sign, right? Now I know it's hard to read these because it's just a bunch of integrals. But what it tells us, especially if we look at just these two right here, okay? What are these equations telling us? This is related to the question that you asked earlier, Ash. Let's start with this equation here, the first one. It tells us that if I have a magnetic field that changes in time, that produces an electric field. But then imagine that the electric field that's produced over here also changes in time. The second equation at the bottom says that a changing electric field produces a magnetic field. If that magnetic field is also changing in time, then you repeat the process all over again. So you start with a changing magnetic field, it produces an electric field, which changes in time, which produces a magnetic field, which changes in time and produces an electric field, which changes in time and produces a magnetic field. And I keep repeating it, but you get the idea. You go in this like little circular pattern right here. I guess it's more like this. You start here, and you go, whoops, didn't mean to do that. You start here, and then you go to here, and then you go down to here, and you go to here, and then you go back again, and you just keep going. And yeah, as you're saying there, it's like an electromagnetic radiation in space. That's what we'll be talking about, right? So basically, like, just to put it like this, what you have is you start off with a magnetic field that changes in time. So you have this. That produces an electric field. This electric field might change in time. So that changing electric field could produce a magnetic field. That changing magnetic field could also be changing in time. So that could produce an electric field. And you basically just, you repeat, right? This whole process becomes cyclical, right? From here, we're basically back to here again, and you just repeat the process, right? That's what Maxwell realized. He realized that as soon as you include this important extra term that came from displacement current right here, you get perfect symmetry in these things, and it's quite literally tells us now that a changing magnetic field produces electric field, changing electric fields produce magnetic fields. And as long as they're changing in such a way that every time that you take your derivative, you don't destroy the function, right? Then this process can continue forever, right? So you can immediately think of functions that you can take derivatives of forever without getting rid of the function, right? Well, what's an example of a function that when I take the derivative, I still have a function that when I take the derivative, I won't ever get 0, basically, right? Cosine, yeah, exactly, right? So if I tell you that I have an electric field and the quantity of the electric field is given by some E max, just some whatever the max value of the electric field is, but it's equal to the sine of something times omega t, for example, now I know that my magnetic field apart from some constants, some other things that we need to do here, the magnetic field is then going to be equal to the derivative of this, so it might be some B max multiplied by, what would it be, cosine omega t. And you can easily imagine that then as soon as I take the derivative of the first one, I get the second one, I take the derivative of that one, I get another one, and it just continues forever. Okay, you get this sinusoidal propagation. You get a wave, basically, right? That's what these things are, they're waves. And, we say light is a wave. Light's an electromagnetic phenomenon. That's where we're kind of going with all of this, and you can kind of see the groundwork for it by just looking at Maxwell's equations. Now, it's worthwhile to see if I have any questions or comments. It's pretty amazing. Especially because it comes from a mathematical... It comes from a mathematical, detail, right? It doesn't need a medium to transmit. That's exactly right. That's exactly right. All this stuff works in free space. Yeah. You need to have something to propagate it, but that's about it. You need to have something to start the propagation, which is an accelerating charge. Let's go back and look at these equations. I want to talk about why they don't look exactly the same. So first of all, let's do the simple part. I already said it, but maybe you remember. What's the reason why when I do the electric flux through a closed surface, I get charge enclosed over epsilon naught, but when I do magnetic flux, I get 0? What's the reason for that? No monopoles. Yep, exactly. We have mono charges, things that have just a single charge. Yeah. Okay, what about these two equations? Why are they a little bit different? This equation, Faraday's law, says that I can produce an electric field or an EMF. Remember, this is just an EMF on the left-hand side here, by having a changing magnetic flux, right? The last equation says you can produce a magnetic field with a changing electric flux, but you could also produce a magnetic field just by having some current, right? Either one will do it. So why does equation number 3, Faraday's law, why is there no current in this equation? Which would have to be, well, it'd have to be a magnetic current, right? So why is that not there? Where's the term in equation 3 for the magnetic current? Yeah, magnetic current's not a thing. That's right. Because after all, in order to have electric current, you need to have charges that are moving, and you don't have magnetic charges, so you can't have a magnetic term here. I will say, though, that if we ever found a charge for magnetism, it would show up right there, and we could presumably then, if we could find a magnetic charge, we could produce magnetic currents, and it would show up right here, and we'd have a complete symmetry between all of them, not just a symmetry in empty space, right? But as soon as you get rid of electric charges and magnetic charges, as soon as you get rid of electric charges and electric currents, they become 100% the same. That would make this whole class obsolete. No, it would just mean that there would be new phenomena, right, that we'd have to add in. Still, all the same phenomenon we're describing here are real, It's just, it would add in some new phenomena. There's a lot of effort being used to produce magnetic monopoles. There's some really interesting things that people have done in certain types of fluids. And I encourage you to read about those things, but no one's ever produced a true magnetic monopole. Anything that people produce is always kind of an approximate magnetic monopole, if you might say. Okay. Yeah, that's it. We're done with that chapter. So we're gonna be talking about the next 2 chapters. We're gonna have to put on hold solving these equations, because maybe you can tell, but the fact that the electric field shows up here and it shows up here, and the magnetic field shows up here and the magnetic field shows up here, means that these 2 equations basically form a set of coupled differential equations, basically, right? And they can be solved. And the solution you get for the electric fields and the magnetic fields is going to satisfy something called the wave equation. And it's going to have solutions that look exactly like this. Not exactly. There's going to be additional terms here. But the point is that we're not going to immediately do that. We're going to hold off on that for a couple chapters while we talk about some other features of electromagnetism. And it'll be one of the last things we do in the class. So probably here in 2 or 3 weeks, we'll come back and we'll solve these equations, basically. So what we'll be doing until then is talking about inductance, and then, yeah, there'll be some kind of kx that shows up in here. That's right, because it'll be a traveling wave. But, so we'll come back to this, and we'll solve them. But in the meantime, what we're going to be doing is we're going to talk about inductors. We're going to talk about alternating current, and we'll come back at the end to discuss those things. The one thing we can talk about really quickly here, that we have about 8 minutes, so we should probably take another break, is superconductors. So superconductors are something that we've discussed a little bit in this class, and I even showed you a brief, very short video about them. But a superconductor, just to say, I'm not going to write anything down. We're just going to watch a video about this because it's a lot better way to understand it, I believe. A superconductor is basically just a type of object that happens to exhibit zero electrical resistance when it's cooled down to a low enough temperature, basically. When the temperature gets low enough, for whatever reason, there's something that happens quantum mechanically relating to pairs of electrons grouping up together, and it causes certain substances to have zero electrical resistance. That means that they can transmit current without any loss. The thing that can happen as a result of this is that some interesting kind of magnetic interactions can occur, and superconductors can be used to kind of levitate things, and that's what you'll see in the video. Yeah, Mr. Meowers, there is a difference, but they are both quantum phenomenon. The question was, is there a difference between that and quantum tunneling? Yeah. They're both quantum phenomenon, though. All right. So, superconductors, zero electrical resistance below a certain temperature. Something that was released recently, actually, in the news. I don't know if you guys follow these things, or if I only get them because I click on side stories or what, but they managed to find what's called the room temperature superconductor. And I think that the value of that will become pretty clear after we watch this video. But the room temperature superconductor that they found required extremely high pressures to maintain it, but it is kind of pretty powerful. All right, so let's look at this video. Did we watch this? I think all we did with this video is we watched a very small part of it. So I'm gonna put a link to this video in the comments. We're not gonna watch this one. We're gonna watch a different one. Okay, so this video, if you really want to watch it, you can. It's great. It's really wonderful. We're gonna try a different one just because I like to do different things, and I've already seen that other video like 20 times. So I found this one from the Royal Institution, and this is a levitating superconductor on a Mobius strip. This is a nice combination of good ideas. Yeah, it's interesting, Nathan. We were talking about that, right? So, like, probably about 2 weeks after we were talking about that, they discovered the first one. We'll talk about that after this. We'll pull up something about that, which is really... How much pressure? Oops. It was a really high amount of pressure. Does it say the number? There it is. 267 gigapascals. 2.6 million times atmospheric pressure. That's just wild. Alright. It must have been fun to figure that out, though. Science is really, really interesting. Alright, here we go. Let's watch this. I have to do this share screen thing where I only share the YouTube, though. If you can't hear it, let me know.
I wanted to show you one of my favourite props from last year's Christmas lectures, which is a Mobius strip.
By the way, Christmas lectures, you know who started that? It was Michael Faraday. Michael Faraday used to do these Christmas... I think I told you this maybe at one point, that he did these Christmas lectures where he, like... You can't hear it? Oh, let me fix it then. Where did it go? There it is. Yeah, we'll start over again. No, they weren't studying for Christmas, Ash. They went to like a show, a magic show. It was like a magic show, basically, except it wasn't magic, it was physics. Yeah, science magic show, pretty much.
I wanted to show you one of my favourite props from last year's Christmas lectures, which is a Mobius strip steel track covered in maybe 2,000 or 3,000 of these super strong neodymium magnets. So what I want to show you is how this track is going to interact with one of these. This is a high temperature superconductor made of yttrium, barium, copper oxide. It's a sort of ceramic material. And a superconductor is something that when you cool it down, in this case with liquid nitrogen, loses all its electrical resistance. So this leads to some interesting behaviours, which I'm going to show you. And to do that, I'm going to need to hang this thing from the ceiling, which I'll do now. Cool. So we have one suspended, super strong, neodymium magnetic Mobius strip track. All we need now is some liquid nitrogen. So we're down in one of the labs at the RI. This is where the liquid nitrogen is stored. Right, that'll probably do. The superconductor is now cooling down, which will take a minute or so. It needs to be cooled down in situ because what I'm trying to get to is to have the superconductor kind of locked into this position. So I need to cool it down in situ above the track. I'm cooling it down past its critical temperature, the temperature at which it will become a superconductor and its electrical resistance will completely disappear, which is about minus 180 degrees. The burger tray is there, maintain a spacing between the superconductor and the track. I mentioned that we're trying to lock it into a specific position, so that is the position that we want it to take up. Just going to slide this off. This is the best way I've found of doing this. If I hold this up quickly enough, you can see there that it's actually levitating on the track. You might be able to see a gap underneath it there, sliding back and forth, levitating. Oh, and okay there. So unfortunately, it warms up quite quickly because obviously the effect only works as long as it's at its superconducting temperature. So what's actually going on there? A good way to start to understand that is to think about how magnets interact with ordinary conductors like this copper tube. So if I just drop this nut through, it falls all the way through very quickly, as you'd expect. If I drop a strong magnet through instead, it takes quite a long time. So the reason that's happening is as the magnet moves through the copper, it induces electric currents in the copper. Those electric currents themselves have their own magnetic field, and that magnetic field will always arrange itself so as to resist the motion that's creating it. And this is the fundamental principle of electromagnetism, that moving magnets near conductors or moving conductors near magnets creates electric currents. Now, because this is not a superconductor, because it has electrical resistance, the currents that are created as the magnet falls through will always tend to die away. So if the magnet were, for instance, to be stopped by the electric currents, those currents would immediately die away and the magnet would start falling again. So what actually happens is it just falls slowly through the tube. If, however, this were a superconductor, those currents would not die away. As soon as you induce them by introducing the magnets into the tube, those currents would remain and would keep going even after the magnet has stopped. So if this were a superconductor, the magnets would basically be locked in the pipe. They would be effectively levitating in the pipe indefinitely. So that's part of the explanation. We're sort of halfway there. I'm going to get onto the track now. And to do that, we saw when I was demonstrating the superconductor on the track down here that the effect only lasted a few seconds. It warmed up too quickly. It warmed above its critical temperature and stopped levitating. The solution we decided on for the Christmas lectures last year was to make a little train/boat thing. So we've got a piece of the superconductor embedded in polystyrene with its own little reservoir for liquid nitrogen. So let's cool this down. Again, I'm going to, not a burger tray this time, a slightly different dish. Carefully pick it up, and I think, so now I can send it around, come all the way back, go back on top. This is why we made it like a Mobius strip, so it can go, so it comes back from the opposite side it went round. So if I just stop it there, so it's kind of locked into position. So it's not just repelling the magnets and hovering. I can sort of pick it up and then stick it underneath as well, and it will hang there. So as I mentioned with the copper, when you induce electric currents in conductors with a moving magnetic field or changing magnetic flux, the electric currents that you create will always have their own magnetic field that resists that change, that resists that motion. So when it's hovering on top of here, and gravity is trying to pull it towards the track, that small motion towards sets up electric currents in the superconductor, which have a magnetic field that resists that motion. But likewise, when it comes around and it's now on the other side, now gravity is trying to pull it away, so that act of trying to fall away from the track sets up a different set of currents with a different magnetic field, which this time attracts it to the track. So whichever way you try and move it, whether you're trying to move it off to the side, up and down towards the track, away from the track, the superconductor will resist that motion, effectively locking itself into position relative to the track, so that the only direction it can move is the direction in which the magnetic field doesn't change, i.e. along the track. So basically, the superconductor can be any kind of magnet it wants to be, or any kind of magnet it needs to be at that moment to keep itself in the right position relative to the track. So this material was a real breakthrough, and possibly the first step on the way to what might be the holy grail of superconductor research, which would be a superconductor that would operate at room temperature or close to room temperature, at which point we might be able to use them to replace all of the conventional conductors like copper and things that we use in all our electrical applications today. And all of those materials, when they conduct electricity, they do it inefficiently to some extent and waste energy. If we could superconduct in those applications, then that would really change the world.
So your question, Ash, whoops. Oh no, I have it, okay. Can you manipulate the distant load takes above the track? My guess is there's a equilibrium that occurs, but in this video here, one thing that he does is he shows that it is possible to lock the conductor. There he goes. Okay, I'm just going to play the part of this video where he does this.
Just levitation. It's not just repulsion. I can rearrange the fluxons and it will be locked in this new configuration.
So is that
like this, or move it slightly to the right or to the left. So this is quantum locking.
Fluxons, that's right. You can watch this video and learn all about fluxons if you want to. There you go, Nathan. Just created a computer case at an internal pressure of 2.6 million gigapascals. That's right. You know, one of the things about resistance, right, is if you have electrical resistance, then you're going to dissipate heat. As he said, you're going to waste some energy, right? And then that wasted energy, of course, inside a computer heats it up, which is why you have to have cooling systems inside of any type of a computer, right? So, yeah, I mean, if we could really find a material that somehow exhibited superconducting properties, unless it's a laptop, what do you mean? Laptops get really hot. Oh, back cooling, yeah, for sure. So yeah, there's all kinds of other applications too, which I mean you can probably tell from the video that you were just watching, and this video has something similar where he has a track that it floats along. You could probably use this as a way to levitate like mag rail trains and stuff like that, right? You could have a rail that is a magnet, and then above it you have this superconducting material, and it'll just kind of float above it, right? So you could create trains that kind of operate with very little resistance, where the only type of resistance that they would feel to motion would be from drag, you know, from air drag. So yeah, good place to stop right now. We'll probably take a break for 10 minutes as usual, and then we'll come back. Yeah, it would solve a lot of problems, right, Nathan? That's right, yeah. So superconductors are a very fascinating field. before we go away, I guess one thing I'll say is that there's a lot of exciting fields in science, and I think one of them that's extremely exciting right now is a field called material science or material engineering, where what people work on in those fields is they basically you engineer materials, right? Instead of engineering like a building, you engineer a material, perhaps at the atomic level or the molecular level, where you're changing and you're producing materials to do things for you, to do specific things for you, right? And within this field is designing superconductors as well, because these superconductors tend to have they tend to not just be a very simple thing. Like helium is a superconductor at like 4 degrees Celsius, but let me see here if I can find the one that is very commonly used, like the one that he's using in that. Well, here's an example of one. So cuprate perovskite. Okay. Cuprate is that, and then perovskite is calcium, titanium, and then there's an O3 there as well, right? There's the one that they show a picture of in your book is some very complicated alloy of, well, here we go. That's a great picture. Yeah, look at these things. Mercury, barium, calcium, copper oxide. Who decided to make that compound? Or that, it's probably an alloy, right? Just little changes here, right? So it looks like you've got calcium, copper oxide, and barium show up here with thallium instead, and with bismuth and strontium here. I think this is the one that's in your book, the one that's like yttrium, barium, copper oxide. I'm probably not even saying these names right now. Oh, here we go. 30 gigapascals, much less. But look at these temperatures over here. This is the critical temperature, right? None of these are even remotely close to room temperature, right? We're at 200 Kelvin, so we're still a good 170 Kelvin off from. But here's liquid nitrogen. So anything above the liquid nitrogen level, you can just cool off with liquid nitrogen. And I would almost certainly guess that one of these up here is what he was using in the video. Yeah, it's pretty exciting, right, Nathan? They're at the point where they're trying every combination they can think of. Yeah, and that's what you do in science, right? You try things, you make tests, and try something different, do a test, and eventually you make very, very, very slow progress. And after thousands of years, who knows what we'll know, who knows what we'll be able to do. Because these, it's exciting. It's an exciting type of science, material science, I believe. So it's very active research, and superconductors is only one part of that. Yeah, diamond is right there. Is it this one? Now, what is? Okay, so this means it's a carbon allotrope. It's cool. BCS. You guys know what a BCS is? There's a whole thing about BCS. Just anyway. All right, let's take a break. It's 8:10 now, so we'll take a break till 8:20.